Good day everyone. We are Group 8 and today we'll be presenting our ECNG 3032 chocolate factory design. On the agenda today, we'll walk through the full chocolate making process, followed by the process flow diagram for the implemented design. Then, the detailed PNID diagram demonstrating the control system implemented in the design, as well as the factory floor plan layout for the machinery placement. And finally, our hazard analysis for the design system.
Let's take a deep dive into the chocolate making process. Our flowchart shows the major stages involved in converting raw cocoa pods into finished chocolate. The process begins with the pod breaker module where the pods are opened and the seeds are collected. The seeds then move to the fermentation module where controlled fermentation develops the flavor precursors needed for quality chocolate. Once fermentation is complete, the beans enter the drying module where they are reduced to about 30% of their original mass. After drying, the beans are sent to the roasting module, which enhances flavor and prepares them for mechanical separation. Roasted beans move to the winnowing module, where the shells are removed and cocoa nibs are extracted. The nibs then pass into the grinding module, which reduces the particle size to below 30 microns to achieve the smooth texture expected in chocolate. From here, the product flow splits. One stream goes to the pressing module to extract cocoa butter, while the remaining chocolate mass continues to the conching module, where viscosity is refined and flavor is developed. The conched chocolate then enters the tempering module, ensuring the correct crystal structure and final consistency. Finally, the tempered chocolate is transferred to the molding module, where bar cores are formed and cooled before the product is demolded and completed. Now we transition into the actual process flow diagram, which gives us a visual aid on how the considered design of the plant is to be implemented. This is our full process flow diagram for the chocolate factory. We organize the system to follow the natural sequence of cocoa processing, starting with raw pod handling on the top left and finishing with chocolate molding and cooling on the bottom left. The layout separates the wet and dry bean operations at the top from the liquid chocolate stages at the bottom, which improves hygiene, reduces cross-contamination, and simplifies ventilation and temperature control. We use parallel conveyors and duplicate fermentation and drying units to support well-ratioed production, ensuring that the factory can process batches with efficient use of machinery. Major transformations are clearly grouped: fermentation, drying, roasting, winnowing, and grinding before the process splits into cocoa butter pressing and liquor refining. The lower section consolidates the liquid operations, including conching, tempering, molding, and cooling. Overall, this PFD was designed to highlight the main material flows, identify critical control points, and ensure that the downstream stages receive a consistent, conditioned feed that supports both quality and efficiency in the final product.
Next, we will talk about piping and instrumentation diagrams. The PNID gives a high-level view of the chocolate production process from cocoa pod intake through roasting, pressing, conching, tempering, and finally packaging. Key instruments such as temperature, level, and flow transmitters are shown on all critical lines, and each of the devices send a 4 to 20 milliamp signal directly into the Siemens S7-1500. These signals are then processed by the PLC's internal control programs, which act as the system's controllers to regulate the various stages of the chocolate production process. Control valves are specified with sanitary designs suitable for food processing and are placed to regulate product transfer between major unit operations, ensuring that the process can be monitored and controlled effectively from end to end.
Now we transition over to the chocolate factory's floor plan layout. This slide shows the full floor plan layout with all the equipment drawn to scale using a 5mm to 1 feet ratio as shown in figure 4 of our report. The layout was designed to match the actual dimensions of each machine, including the pod breaker, hopper, fermentation units, dryers, roasters, winnower, grinder, hydraulic press, butter culture, heat exchanger, temperer, dispositor, and molding equipment. We arranged the plan to ensure a smooth linear material flow from raw pods at the end left of the room to the finished chocolate product at the right. Dry bean processing equipment such as fermentation boxes, dryers, and roasters were grouped on the upper section of the layout, while downstream liquid processing equipment like the concha, butter tank, temperer, and depositor are positioned on the lower section of the diagram. The separation improves hygiene, ventilation control, and heat management. Pathways between the equipment were intentionally left open to support safe operating, access, maintenance, and material handling. The equipment spacing also reflects real-world clearances required for cleaning and inspections. Overall, the layout supports the continuous processing, minimizing cross-traffic, and ensuring that the final installation will be both efficient and easy to operate.
To protect the safety of the equipment and all people involved, we conducted a hazard analysis, where we analyzed the causes, consequences, safeguards, and recommendations for no flow, higher temperatures, lower temperatures, and higher levels. In this presentation, we will analyze higher temperatures and higher levels. Multiple machines involve the use of temperature control. Factors that can cause higher temperatures include temperature control malfunctions, faulty temperature sensors, heating element malfunctions, or exhaust fan malfunctions. These can cause the heating element to provide excess heat or affect the efficiency of the exhaust fan. Consequences range from damaging equipment, off-spec product, flow disruption, and pump damage, since the equipment was not designed for unexpectedly drier compositions. It can also cause a potential fire. Safeguards include installing low selector selective control, override temperature control in the control loops, safety interlocks to trip heaters if exceeding set temperatures, and critical priority alarms to command immediate operator actions to maintain safety. High-level deviations can be caused by malfunctioning level controllers and sensors. Failed valves can also cause blockages to the tank outlet and surplus product into the tank inlet. The main consequence of this is product spillage. This can lead to equipment damage, sanitary contamination of the environment, slippage hazards for workers, and an off-spec final product due to contamination. To avoid this, we can install control loops with high selector selective control, override controllers, and safety interlocks to trip the inlet valves to avoid over-intakes. We can also install containment walls around tanks. High priority alarms should be installed to alert operators to act where necessary. For all deviations, it is recommended to perform a layer of protection analysis to assign an appropriate safety integrity level for the protective systems. And now we will be answering our questions.
Explain the operation of the control system for the fermentation step. During the fermentation stage, the control system treats each of the 3 fermentation boxes as an individual timed batch. The number of boxes is chosen so that the total capacity matches the throughput, while each batch remains small enough for efficient, well-controlled fermentation. Once a box was filled with wet beans, the PLC starts a fermentation timer and continuously reads temperature from probes in the bean mass. For each box, the measured temperature is compared with a set point, and the corresponding aeration blower speed is adjusted to retain or remove heat, keeping the conditions within the target range. Operators may still turn or mix the beans if required, but the feedback loop provides stable conditions. While the timer is below the required duration, discharge equipment is interlocked. When the set time has elapsed, the PLC flags the batch as fermented and allows beans to transfer to the downstream dryer.
Identify a type of signal converter used in a project and explain your choices for the specification operation ranges. So for this one, our instrumentation needs a few signal converters so everything matches the Siemens control system, which is built around 4 to 20 milliamp signals. We use interposing relays to safely isolate the PLC's digital outputs from the motor starters and the on and off Burkett valves. The 2 weighing scales communicate over RS-232, so we added RS-232 to the Profinet converters because the S7-1500 can't read RS-32 directly. The torque sensor outputs a low-level millivolt to volt strain gauge signal, so we use the HBM conditioner like a ClipX or a PMX to convert it into a standard 4 to 20 milliamp signal. For the PLC, all other transmitters, temperatures, levels, and flow are already provided in the range of 4 to 20 milliamp outputs, so they connect straight to the PLC with no extra conditioning.
The layout was done in a way to follow the natural order of creating cocoa, so that each nearby machine feeds into the next with minimal handling. This reduces any contamination risks and sets up the factory for maximum efficiency. All machinery in the factory was sized according to the manufacturer's specifications, and the layout was designed to maintain safe and functional spacing throughout the production area, maintaining a clearance of 6 to 12 feet between each major piece of equipment to ensure easy access for routine operation, cleaning, and maintenance. All walkways were clear to avoid any safety hazards such as tripping and to facilitate safe evacuation routes. These factors influence our choice of equipment layout, as we sought to balance efficiency, safety, and long-term maintainability.
Finally, question 4. How we sized and determined the factory's pumps. The pump selected for the factory is the Fristam FPR 701. The flow rate was chosen to be 10 GPM. Using Bernoulli's equations, as seen on the slide, the required pump head for each transfer line was calculated, and all processes were found to need between 1.1 meters and 1.89 meters of head. The FPR 701 easily meets this requirement, providing up to 10 meters of head and a maximum flow rate of approximately 26.1 GPM. In addition to the hydraulic performance, the pump's sanitary, low-shear design helps prevent overheating of the product during transfer, making it ideal for food-grade processing environments. Thank you for listening to our presentation.